This section is part of hypothesis testing. What I'm going to do is go through some major concepts in hypothesis testing and go through each one much more systematically than I've done already. And these are the concepts of statistical significance, effect size, decision errors, and statistical power. So I'll go through each one of these and explain them in more detail. Okay, here's the fundamental situation of hypothesis testing. And this is part of what I'm going to talk about in effect size. So here you have a basic hypothesis testing situation. You have population 1 are 5th graders who receive special instruction of some kind. In population 2 are 5th graders who receive no special instruction. And then you have some sort of dependent measure like reading skill or performance in a class or something like that. But these are your two conditions and your two populations. Now your research hypothesis is that population 1, graders who receive special instruction, will be greater than population 2, those who don't receive special instruction, on some dependent measure like performance in a class. Then the null hypothesis is that the two populations will be the same. So you have a basic hypothesis testing situation in which you have two groups being contrasted, and you're going to try to figure out if the results you get when you actually sample from them indicate that there's a difference, and this difference cannot have occurred by chance. Well, let's look at this situation. You've got the two groups, and we're comparing 5th graders who receive instruction to those who don't. Imagine if you run this study, you get a sample with a mean of 220. You can tell that the 220 is way off the mean and standard deviation of the comparison group. You conclude there was a significant difference. So it's very unlikely this 220 would have occurred by chance. The 5th graders who got instruction did 20 points better than the population who didn't get instruction. That beats a 95% confidence interval, so you conclude that the result is unlikely to occur by chance, and instruction, has all these great effects and so on. And let's take another group. You do the study again, and this time you get a mean of 210. Well, a mean of 210 is still statistically significant. So both of them are statistically significant. So the group that gets treated with instructions this time has a change of 10 points from the mean of people who don't get instructions. That's still unlikely to have occurred by chance. They're both significant. But obviously the former group that got 220 did much better than the other group. But nothing in my study is going to allow me to compare that so far. If all I'm examining is statistical significance, then all I can conclude is that they didn't occur by chance. I can't really say much about the magnitude of the difference. Well, the study of the effect size allows me to comment on that. And not only is there a result that beat chance, but the result of a certain magnitude. The change associated with the intervention is a certain size. Now this is crucial in understanding the results of a study. If all you conclude there was a significant difference, you may have discovered a very small, in a sense, clinically insignificant sort of change, even though it beat chance. And if you're say doing a new medication for treatment of an illness, and it only affected people a small amount, you may have beat chance, but I want a drug that cures people. I don't want a drug that just makes them a little bit better. And even if that little bit did not occur by chance, it's still it's not impressive. One of the problems that the FDA has is examining different types of drugs for their effect sizes. Lots of drugs will show statistically significant effects, but there's probably just a few of them that are really making an impact. And if physicians aren't told this, they'll just see a field out there of 10 drugs to pick from, and over time, after they picked all 10 themselves and done their own kind of informal research, they'll figure out which one works and which one doesn't. And a lot of times, the effectiveness of things like antibiotics and pain medications and things like that are more disseminated by word of mouth than they are by research studies. Well, at any rate, effect sizes allows you to examine this, and the study of effect sizes influence on the application of statistics recently. Well, what is the effect size? Well, as this graphic shows, the effect size is the amount that the two populations are separated. So when you look at the distributions of two populations, and they're different, they're separated by some magnitude. That's an indication of the effect size. Because again, in our hypothesis testing, We're comparing two populations. In this example, it's a population that gets some kind of special training versus a population that doesn't, and they're going to be displaced by some magnitude. And that displacement, that difference, is the effect size. Now, if you notice here, these two populations are displaced. You can see where the displacement is really being defined by how far apart the means are and how much the distributions overlap. Now, notice that there's still quite a bit of overlap in these two distributions, probably statistically significant. So this distribution difference, or this effect size, probably did not occur by chance, but you can also see that the effect is not that large, that the two groups are still overlapping quite a bit. People who don't get instruction, for example, are still doing quite well compared to people who do get instruction. There's still a lot of people who probably, pass all the tests and do well, they're getting this instruction. It's just that on average, the people who are in the intervention and one are significantly different on average than another population. And that magnitude of difference is the effect size. Okay, here's some other points about effect size and how to calculate it. Now remember, effect size is the amount that the two populations are separated. One of the neat things you can do with effect sizes is compare effect sizes across studies, even if the other studies use different sample sizes and different dependent measures. There are ways of standardizing all these that you can actually compare a study, say, of these two groups of children that used, say, a spelling test versus a study that used their class grade. And you can actually standardize both of the dependent measures, calculate effect sizes, and compare the effect sizes for those different domains. So that's one neat thing you can do with effect sizes. The last reference on the slide here is to studies that use different metrics. So some study might use a different kind of dependent measure that actually scale differently. We can adjust all these scalings so that you can actually still compare the effect sizes directly. And I'll explain that in a couple of slides ahead. Okay, well, how do we actually calculate effect sizes? We have a sort of a theoretical and abstract idea that came from the previous slides, which is a reflection of how far apart the two populations are. But we need a score. We need an actual metric that calibrates this. Well, Cohen developed something called Cohen's d, which is a standardized effect size. And this is the raw score difference between the populations divided by the population standard deviation. Now, the populations can have different means and standard deviations. Remember how we could compare different studies that may have actually used different dependent measures? So each mean and standard deviation of a population will be calibrated for different scores pertaining to that population. So in study 1, we were comparing students who got special instructions versus those that didn't. And we knew from our study that the mean of the population was 200. The standard deviation of the population was 48. And so we went out and did our study, and we discovered that children who were treated ended up with a mean of 220. Well, there you see the 220. So we take 220 minus 200. Remember, 200 is the population mean for children that are not treated. And then we divide that by the population standard deviation. So we take 20, which is a difference score, divide that by the population standard deviation, and we get a ratio here of 0.42. Now we go out and do another study which uses a different metric for its dependent measure. So say the first study used a dependent measure of, say, of a spelling test score in the class. And the second study is going to use some other kind of score, say a reading score in the class. And so we have here a population mean of 160, and our study mean, the group that was treated, has a mean of 300. Well, that looks really large, but if you look at the standard deviation of the population, it's really big. So there's a lot of variability in this population, and this population is very broad. It has a lot of high values and low values, and not so many in between. So it has a standard deviation that's very large compared to the mean of the population. But then when we do our arithmetic here, you would think with a difference of, 140, that would be a big, big difference. But it turns out that because the standard deviation is so large, because there's so much spread in these distributions of these two populations, we end up with a ratio now of 0.66, which is a much smaller number. So it's bigger than 0.42, so still the effect size for this study is larger, but it's still not as big as you would expect given the raw score difference between the means. Now, if you look at these two, you can see where you can compare them. So the second study had a larger effect size than the first one. Even though they used different dependent measures and they used different populations of these dependent measures, where you saw a big difference here in the means and standard deviations of the populations, we have now standardized this. We've now brought those differences under control. We've qualified them mathematically, and we've gotten a general index by which we can compare the two effect sizes directly and draw a conclusion that one effect size was larger than the other one, because now they're on the same metric. You can see if you were referring back to raw scores, it'd be really hard. The first study's got a 20-point difference in raw score. The second study's got a 140-point difference in raw score. They seem like they're very, very different, but because the standard deviations are so large, the variability within the populations is so big, in the second study, it actually brings down the calculation of Cohen's d to a level that's actually kind of close to 0.42. They're really not that different. Size conventions for effect size. Well, one of the problems that came up early on was how do you conceptualize the magnitude of an effect size? And Cohen's d gives you a number. It gives you an index of how different the populations are, but it doesn't really give you an index of how big that number is, how big, the separation is. Cohen also proposed then some size conventions in which 0.2 would be a small effect size, 0.5 would be medium, and 0.8 would be large. So just sort of have those in your mind as demarcations. There's nothing firm about these, though. For some applications, I think what he's referring to as a medium or small effect size might be actually a big effect in terms of how productive it is in changing something, or the population displacement clinically, in a sense, or how meaningful a change is. Can be quite small, but still be quite significant. It's not like in every situation you're looking for a cure all the time. If you just have a big effect, statistically significant effect that's medium size, that's wonderful. And effect sizes that are larger are something that's not even expected. Okay, the next concept in this section is statistical power. This is an interesting name for something. I'm not sure what the word power really has to do with anything, but it's a good name for identifying this. The statistical power is the probability that a study will render a significant result if the research hypothesis is true. Now, you should etch that in your brain. It's very easy to ask a test item about that on the midterm or the final. It's the probability that your study will render a significant result if the research hypothesis is true. Okay, let's imagine the true situation. You've got a drug that treats, and say you have a new antibiotic that treats an infection, and it actually works. The true situation is that it actually works. You go out and do a study, and you're going to go out and collect your sample and analyze your data, and you're going to figure out if you have an effect size. Did I reject the null hypothesis and support the research hypothesis, or not? Now, you can imagine doing a study in which there is a significant finding that you don't discover because of the way you did your study, or just by chance you pulled in a sample of people that didn't represent the true difference. Well, there's always a probability that even if there's truly a difference out there, you won't find it. And that's the statistical power. Statistical power is the probability of finding a difference, a contrast that's true. Okay, so when you reject the null hypothesis and do your hypothesis testing, you're going to either find a true result that's out there or not, and the statistical power is your probability of doing that. So even if the research hypothesis is true, it doesn't guarantee that you'll find a result. It doesn't guarantee. Obviously, if you're out there sampling and so on, just by chance, you might pull in people that don't have a difference. And that occurs all the time. If the research hypothesis is false, you do not want to get a significant result. If you did get a significant result, what kind of error would this be? And I want you to try to answer that question. I'll talk about this, also the answer to this question, in a couple of the slides. But just think about that. If the research hypothesis is false, you don't want to get a significant result. So if the null hypothesis prevails, if there's not a difference out there truly, or if your antibiotic's not effective, by chance you'll go out there and collect people in your study and so on that are in the high ends and the low ends of the distributions and so on that actually show a difference. And you'll calculate your mean difference. It'll be statistically significant. When in truth, just by chance you've been snookered. Just by chance you've been fooled into thinking that your intervention is actually effective when it isn't. And you got to think about the name of that kind of error. Okay, so power is a major criterion for examining the validity of a research study. When I go out to propose research to granting agencies, my study has to have significant power. It has to have enough power to find a result that's out there, that's really out there. Imagine if you went out and proposed a study and got a lot of money from the government to go study something when you didn't have statistical power, when the probability of finding something from your study design is actually quite low. Well, the government shouldn't fund you for research like that. If you're going to go out there and do a study to try to find something that's really out there, some difference that's really true, you need to design your study so the probability of finding that is pretty high. Now, I'm going to talk about the different factors that figure into this. A real important one is sample size. Imagine if you just went out there with a sample size, 5 subjects or something, a very unstable sample. Your probability of finding a significant result when it's really out there is actually quite low. Statistical power. Now we're going to move further into figuring out how to actually calculate statistical power. It's a pretty complicated idea. It's not an easy concept to master, I think. I think the definition of it seems clear enough, but when you actually get down to actually calculating this probability, it starts to get a little daunting. Now it does rest, however, on the old normal curve and probability judgments that are based on the normal curve. And here you have depicted 2 normal curves. The first one is a depiction of a situation where the research hypothesis is true, so it's correct. Now again, remember, the power is the probability of finding a result when the research hypothesis is true. So there's really an effect out there, and this is your probability of finding it based on the nature of your study. Okay, so the first distribution up there shows the situation when the research hypothesis is true. So here you see the distribution displaced to the right. And it's displaced to the right, presumably in a significant direction. And the bottom one is showing us the distribution of means if the null hypothesis is true. So if the null hypothesis is true, you have the mean sitting over 200, which is the population mean, and there's apparently no difference between the two populations. Now let's look at the shaded areas. Well, the alpha down there is shaded, right, where the null hypothesis is. The alpha level represents the probability, the statistical significant probability cutoff. So in that part of the distribution, if a mean falls there, it's very unlikely it occurred by chance. Now you extend this alpha level of 209.84. That's the cutoff level for probability of 0.05. Now if you extend that upwards, you see it meets the raw score line at the appropriate place at 209.8. Now if your other population mean is significantly different than the null mean, the untreated mean or whatever, the group that doesn't get the intervention, the two distributions would line up and you wouldn't have any significant result. But here we've got levels, above 209.84 that are statistically significant. And the true situation is that the populations are different. When you extend that line to the score levels and the distribution at the top, power represents the area of the curve for all those levels of the result that will be statistically significant. And so the area of the curve associated with those levels is the probability of finding a significant result when it really exists. Okay, again, you've got areas under the curve representing probability. And you can see where you choose your cutoff level of 0.05. And you can see when you extend that up to the true situation, where the research hypothesis prevails, there really is a difference between the groups. Then the part of the upper curve that's colored in represents the area, and it represents the area of the curve that's assumed by those values, and that area is the power. Now imagine if you took that distribution to the top and moved it further to the right, which would indicate that the effect size, the difference between the two means, is even larger. Well, you notice then that the gray level, the gray area, would be much larger. And we'll talk about this in a second, but basically your effect size is the difference between your means. If it's a big difference, it's easier to find than if it's a small difference. But we'll talk about that in the future. Right now, just think about the area under the curve for mean value past the criterion for the 0.05 level. The probability of finding those is the area that you see in the upper graph. Okay, in this next image, we have the same basic situation, but it's expressed slightly differently. Here, statistical power is also expressed as the area under the curve for the scores that would be in the alpha range, but it's framed as a certain kind of question. If you were to take a random mean from the top distribution, how likely would it come from the shaded area? So you can see the shaded area is a little bit less than half, so it must be a little less than 50% likely that the mean taken from the top distribution would come to the area at the top. Well, that's the probability of finding a value in that range, since all the shaded area is subsumed by that range. If you were to take a random mean from the top distribution, the probability of getting one in that range would be power. Now here you see a very similar slide to the last one, except that the top distribution has been moved over further to the right. So when you do that, more area of the curve is now shaded. There are more values under the curve that correspond to the alpha level or the p-value. So now you're going to ask the same question. If you were to take a random mean from the top distribution, how likely would it come from the shaded area? Well, here, of course, is far more likely. If you pick something at random from the top there, it's far more likely that a randomly chosen mean will be within the shaded area. So now when you move the distribution further away from the null hypothesis, the probability of finding a value in the shaded area goes up. It now becomes more likely. Now this is an indication that as you change the effect size, as the distributions are moved further apart, the probability of finding that difference, if it really exists, increases. And so the area under the curve increases, and it's now more likely that you will find an effect. And that makes sense. If there is an effect out there and it's large, it ought to be easy to find. You shouldn't have to see subjects to represent that effect if it's large. As it becomes smaller and smaller, it becomes less and less likely that you'll find it. Okay, now we're going to do one of those interactive programs again, because we're going to manipulate things like effect size and alpha levels and stuff and see what happens to power. And a good way to do that is just to have a program that lets you change all these things interactively, and then you can see what happens rather than having static images. So go to the web link indicated here on the slide. It's at a site called learnpsychology.com. Go to courses, statcourse/programs.htm, and you should see a list of programs at that website. Download the program called Power and Effect Size. Just have to click on it. When you download it, I would download it to the hard disk, download it to the desktop or someplace where you can see it later, and then run the program by double-clicking on it or using the run command in Windows if that's what you're going to do. And again, make sure you download the correct version that you want to run. If you have a Macintosh, download the Mac version. If you have a Windows computer, download the Windows version. After you get it running, it should look like the display here. Click on the instructions button to learn about the program. You should be able to understand the instructions, I think, and you'll get a feel for what the program is going to let you do. Okay, notice in the simulation that there's a slider under the top distribution. Notice there's a gray line with a blue dot there. If you move that blue dot around, it'll move its position on the gray line. So click on the blue dot and move the slider to the right. When you do this, you'll notice that the upper distribution will move. It'll move relative to the lower one. And what you're actually doing here is artificially creating the effect size to be larger and smaller. So move that slider to the right, the distribution will follow, and you'll notice that more of the upper distribution is now red. And that indicates that the probability of finding a difference this large has now increased. Keep moving it to the right, moving it to the left. See what happens to the red area when you do that. The red area indicates the power. It's the probability of finding a score in that range when there really is a difference between the two distributions. The next thing you should do is change the alpha level, change the p-value, and you'll notice that the power increases when the p-value is larger. If you set the p-value to 0.01 instead of 0.05, you'll notice that the probability of finding an effect is now decreased. It doesn't seem to decrease very much, but it is an important factor. The p-value can be a very important way of becoming too conservative in your study and not finding effects that are actually there. Then the next thing you should do is change the standard error of the mean. When you change the standard error of the mean, it makes the mean narrower, makes the distribution narrower. And when you do that, it generally increases the probability of finding an effect if it's actually there. And you'll notice that when you set the slider with the standard error of the mean smaller. Well, now we have a sense for the theoretical model of power. We're going to go through the steps of actually calculating it. And remember, power is the probability of finding a significant result when it's actually there. Okay, well, here are the steps. First, calculate the mean and standard deviation of the comparison distribution, population 2, and the predicted mean of the population given the experimental procedure, population 1. So we need the means and standard deviations of those two distributions. Next, figure out the cutoff score on the comparison distribution in order to reject the null hypothesis. Now, this is probably going to be at the 95% level, and what you want to do is go to your z-score table in this situation. Go to your z-score table and figure out what the cutoff score is going to be with the 95% level. So that's going to be in a table back in your textbook or any other table of z-scores. Now figure the z-score for the same point, but do this on the distribution of means for the population that receives the experimental manipulation, population 1. So this would correspond to the distribution at the top of these displays that we've seen, these graphs that we've seen before, and on the simulator. So you find out where that z-score is, and then using the normal curve table again, then figure out the probability of getting a score more extreme than that score. So if you discover, well, z-score of 1.64, I think it is 95% level. If a z-score higher than that is, you just need to figure out the probability of z-score higher than that. So you need to go to the table, just like we've done before when we found percentiles. Find the percentage level that corresponds to that z-score, and the percent under the curve that corresponds to it or higher is the power, the probability of finding a z-score in that range or higher. And so now you've calculated power. It's relatively simple to do if you have the z-table. It's virtually impossible to do by hand, just by calculation. You need to be able to figure out areas under the curve, and all that's been done for you and put into a table. Here's an example of calculating power. A large organization wants to start a new health promotion program that will educate employees about exercise, smoking, nutrition, and so on. The industrial organizational psychologists are asked to conduct a study before the program is put in place throughout the organization. 80 employees will be randomly selected to receive the program. Their general health will be measured at the end of the year. So now general health is a dependent measure. It's the thing that you're going to compare, test the hypothesis on. And now you're going to have an intervention program. And it would be nice to know if the effect sizes are relatively large. If you have a program like this and it costs a lot of money, but it doesn't really change things very much, then it's probably not worth doing. And so we have to do a study like this to figure that out. The first thing we need to know is what's the probability of finding a significant result in a program like this if it really exists. Okay, now to continue the example for statistical power. Step 1, calculate the mean and standard deviation of the comparison distribution, population 2, and the predicted mean of the population given the experimental procedure. In this case, it's the health program. Okay, well, the general health test, which is the dependent measure, was normed, and the population has a mean of 58 and a standard deviation of 14. Now, it's pretty unusual to have known population parameters like this in the real world, but to make these calculations and comparisons easier, this has been given to us. So we have a mean of 58 and a standard deviation of 14 for the general population. The predicted mean will be set to 63. This is the minimum level of change that makes the program worth doing. If we don't get a general health index change up to that range, then it's not worth doing. And you could imagine that. I mean, if you're proposing this new program and it costs money to do and takes people away from their work schedule, if it doesn't really change their life, there's not much point in doing it, even though it might sound good. Okay, well, now the variance of the population is 14 squared. We'll need that for some calculations later. So remember now, the square root of the variance is the standard deviation. So if you square the standard deviation, you get the variance again. Okay, the variance of the distribution of means, the comparison distribution, is 196, which is the number we just got by squaring the standard deviation, divided by 80, which equals 2.45. The standard deviation equals the square root of 2.45, which equals 1.57. So now we've got the mean and standard deviation for the comparison distribution. That's going to enable us to calculate probabilities. Okay, step 2. Figure the raw score cutoff of the comparison distribution to reject the null hypothesis. For the 5% level, one-tailed, the z-score cutoff is 1.64. A z-score of 1.64 equals a raw score of 60.57. In the lower curve, there's a shaded region to the right of the number 60.57. And this is referred to as the alpha region in that lower curve. So the alpha region represents the area under the curve is subsumed by the score that's at the cutoff level or greater. So scores in this range are unlikely to occur by chance. They only occur 5% of the time or less. And that equals a z-score of 1.64 and a raw score in this particular case of 60.57. Okay, step 3. Okay, for step 3, we're going to figure the z-score again for the same point, but now we're going to do it on the distribution of means for the population that receives the experimental manipulation, population 1, the one on the top there. So we're going to run that score up to the level on the top distribution, find out where it's where the corresponding z-score is for an alpha level of 0.05 on the bottom distribution, and then we can figure out power once we do this. Okay, so on the upper curve, a raw score of 60.57 equals a z-score of, and here we have to do some calculation, take the 60.57, subtract it from 63, divide by 1.57, which equals a negative 1.55. And then note the shaded area in the upper curve. Okay, so once you run that line up there, you figure out what the cutoff is going to be up there for the power level. And that's what you see depicted in the graphic. And notice that the power level now has been shaded. And see how the power level and the alpha level correspond? But in the upper distribution, you have a difference, a real difference that's occurred in the environment. It's really out there, and you're trying to discover it. Well, the values that represent that real difference that you can find are the ones past the alpha level. And the area of the curve that subsumes those values in the upper distribution is the power level, the power probability, the probability of finding a significant result when it's actually out there. Now we're on step 4. Here, use the normal curve table and figure out the probability for the z-score that you got that's more extreme in your cutoff. Now, whenever there's any instruction called figure out the probability, that means figure out the area of the curve. Now, obviously, you can't do that by hand. That requires some calculus. So there's the levels for parts of the curve, for cutoffs and things like that. For major scores on the curve are already calculated, and they're in tables. So you need to go to the z-score table in the back of your book and look up the percentiles that correspond to those z-scores. Well, when you go back in that table, the normal curve table shows about 44% between the mean and a z-score of 1.55. The area to the right of 1.55 equals 44% plus 50%. Remember, you still got half the curve there, which is a total of 94%. And you can see that's a lot of the curve. So in this case, power is equal to 94%. So 94% of the curve is between your cutoff z-score or higher. And that area corresponding to those scores is the power. So that's the probability. It's 94%. Now beta, which is the inverse of power, is 100% minus 94%, which equals 6%. And we'll get to what beta means in a little while. But beta is sort of the opposite of power. Beta is the probability of finding another kind of result. And we'll talk about that in another slide. All right, now you've calculated power. Now we're going to talk about what kind of things influence power. Again, power is the probability of finding a significant result when it's actually present. And obviously that's very important to calibrate before you do your study. You want to make sure you design a study that's going to find an effect if it's really there. Well, the first thing that affects power or influences power is effect size. And if you look at these two graphs, these are the two illustrations from the example before. The one on the left, the graph here on the left, shows a situation in which the two populations are actually quite close. So the effect size is not very large. Well, you can see in that situation, the power, the area under the curve in the top figure, is relatively small. It's less than 50%. So the probability of finding a small effect is itself small. If you go to the graph on the right, you see when you move the two distributions further apart, the probability of finding those scores that are different is much greater. So a large effect size is easier to detect. Now that makes a lot of sense, because if you're out there doing a study and you have a large effect size, that means a lot of scores in the second distribution representing the research hypothesis. A lot of those scores will be statistically significant because they're way out there. They're very far from the mean of the null hypothesis. But if you go to the graph on the left, you see where those means are closer. So there's fewer scores that are going to be significant. And the more scores that are significant, obviously the greater the curve that they will subsume, the greater the curve area they will subsume, and so the power itself will be larger. So the probability of finding a significant result is greater, the power is higher, if the effect size is greater. Here's another influence on power. Imagine you have two distributions like this, and the variance is much smaller in each one. So if the standard error of the mean is smaller, or the variance across these two groups is smaller, it will make the two groups more distinctive, and that serves to make the power higher. So you notice here, if you compress these two distributions, even though the means are not that far apart, if you shrink them in, make the variance smaller, you'll increase the area of the curve graph that represents the probability of finding the significant result there when it really exists. Again, this makes the distributions more distinctive from each other. It separates them more. And anything that separates them more will cause power to go up. It will be easier for the experiment to detect. So the things that make variance smaller are, sometimes variance is what it is. But if variance is being affected by things like unreliable scores, so if you have random variation in the scores that are being used for the dependent measure, that will tend to disperse the distributions. So one way to increase your power is to choose measurement tools that have high reliability, that are consistent, so that you don't have error variance in there, making things murkier than they actually are. So the mean difference between the two, as well as the variance, figures into the effect size. And again, if the effect size is high, then you have higher power. So it's easier to detect differences that are large than it is to detect differences that are small. A great influence on power is sample size. The greater the sample size, the smaller the standard deviation of the means. And remember the simulation we did where we estimated, where the sampler grabbed means from an upper distribution that was blue and plotted them in a distribution down below? Well, the sample size is small. Small sample sizes are unstable estimates of the population parameters. And so there's a lot of variability you have to take into account because small samples will misrepresent the mean and the variance of the population. Large samples, though, represent it pretty well. They represent it very well. And so the larger the sample size, the smaller the variance in the distribution of means. If the distribution of means is narrower, then there's less overlap between the groups. And that makes the two groups, like you see here, more distinctive looking. It makes the effect size larger, and these, of course, independently influence power, sample size, and effect size. But if I use larger sample sizes, I will estimate the population parameters better. That distribution will be narrower, and so we'll have greater power. We'll have more likelihood of finding a result when it's actually out there in the world. So in the ideal situation, where you really want to maximize power, maximize your chance of finding a significant result when it's actually there, is to have a relatively large sample size, as large as you can practically collect, up to a certain point. You only need a few hundred subjects probably to represent large populations. If your sample size is smaller than that, you need to work whatever magic you can to bring your sample up to a reasonable number of subjects to represent the population. And the second thing you want to do is use measurement. Use in your dependent measure, make sure you use measures that are highly reliable. If measurement has random variation in it, random error in it, unreliability in it, then you'll tend to produce variance in the two populations, or in these two comparison groups. You'll tend to have variance that's coming from chance factors, and that'll make the groups more spread out, making the effect size smaller and harder to detect. So again, power is the probability of getting a significant result when it's actually there. And again, you want to do this when you plan your study. Make sure your power is reasonably high. If the part of the curve isn't going to be, at least 50%, at least, covering half the curve and probably more, you can do yourself out there and study something, but the chances of finding a significant result, are pretty small. So either your sample size is too small, your measures are unreliable, and your effect sizes are relatively small, and things like that. Going out and try to find a small effect size with a small sample is extremely hard to do. And you'll end up getting negative results, and then concluding, you won't reject the null hypothesis. You'll conclude there's no effect out there because of the way you designed your study. So again, what you want to have is relatively large samples, highly reliable measurement, and of course you want to hope that your effect sizes are large. A lot of times in the research, of course, you don't really even know what the effect size is going to be. You're proposing it to be moderate or high, but you won't actually know until you actually do your study. So your prediction is the way you control your power then is through controlling your sample size and your reliabilities.